Implementation of the Mars Sample Return Mission by 2026, a comprehensive report. Overview. The Mars Sample Return Mission MSRM is an ambitious project that aims to collect Martian soil samples and return them to Earth. The mission involves a collaboration between NASA, the European Space Agency ESA, and the Japan Aerospace Exploration Agency JAXA. With a projected budget of approximately $3.1 billion and a targeted implementation date of 2026, this mission marks a significant milestone in interplanetary exploration. The study of these samples will advance our understanding of Mars geology and assess the planet's potential for harboring life. Key phases of the mission. The Mars Sample Return Mission is structured into 4 distinct phases, each critical for the successful return of Martian samples. 1. Sample collection. The initial phase involves the collection of soil and rock samples from the Martian surface. NASA's Perseverance rover, which successfully landed on Mars in February 2021, is equipped with advanced tools for sampling. It has been actively collecting and storing samples in sealed tubes for future retrieval. The choice of sampling sites is crucial as scientists aim to select areas that offer insights into the planet's history and geology, especially regions that may have preserved signs of past life. 2. Sample retrieval. The second phase is to retrieve the samples stored by the Perseverance rover. This phase is unprecedented in space exploration as it entails landing a retrieval vehicle on Mars, collecting the samples and subsequently launching them into Martian orbit. This operation requires meticulous planning and execution as it involves navigating the rover to the sample collection site, ensuring a safe landing, and employing a launch system capable of sending the samples back into space. 3. Transportation. Once the samples are in Martian orbit, they must be transported back to Earth. This phase includes launching a return vehicle that can travel over 33 million miles and safely re-enter Earth's atmosphere. The transportation phase is one of the most complex aspects of the mission, necessitating innovative engineering solutions to ensure the integrity of the samples during transit. 4. Analysis on Earth. The final phase involves the detailed analysis of the returned samples. Scientists will examine the Martian soil and rock in laboratories on Earth to gain insights into the planet's geology, climate, history, and potential for life. This analysis is anticipated to yield groundbreaking discoveries that could inform future manned missions to Mars and enhance our understanding of the solar system. Budget and timeline. NASA Administrator Bill Nelson indicated that initial budget estimates for the Mars Sample Return Mission ranged from $8 billion to $11 billion. However, due to fiscal constraints and the need for efficiency, the goal is to streamline the mission to fit within a budget of approximately $3.1 billion. The revised plan aims for a sample return by the early 2030s, significantly ahead of the previously anticipated 2040 timeline. Funding breakdown. The budget will be allocated across various mission components, including development and operation of the Perseverance rover, design and construction of the sample retrieval vehicle, launch and transportation systems development, Earth-based laboratories for sample analysis, international collaboration. The Mars Sample Return Mission is a prime example of international collaboration in space exploration. The International Mars Architecture for Return of Samples Mars Task Force has been established to coordinate efforts among NASA, ESA, JAXA, and other participating nations. This task force focuses on integrating scientific objectives with engineering challenges to ensure successful mission outcomes. Roles of collaborating agencies. NASA, leading the mission with the Perseverance rover and overseeing the overall mission architecture. ESA, contributing through its expertise in launch vehicle development and Earth-based sample handling facilities. JAXA, providing technological support particularly in aspects related to launch systems and mission design. The Mars Task Force has convened multiple times to align the scientific goals of the mission with the technical requirements, ensuring that all parties are on the same page. This collaboration exemplifies the global interest in Mars exploration and the shared goal of advancing our understanding of the planet. Integration of information. Both NASA and ESA emphasize the mission's critical role in understanding Mars. The scientific value of return samples cannot be overstated, as they will provide direct evidence of the planet's history. The collaborative nature of the mission further enhances its potential for success, leveraging international expertise and resources. Summary of key insights. The Mars Sample Return Mission is positioned as a high priority for planetary exploration with potential implications for life beyond Earth. The establishment of the Mars Task Force signifies a commitment to international cooperation in achieving complex space missions. Timeline of events. 1993, the International Mars Exploration Working Group (INUG) is formed to facilitate international coordination on Mars missions. 2001, ESA launches the Aurora Exploration Program, laying the groundwork for future robotic and human exploration. 2021, the Perseverance rover lands on Mars, beginning its mission to collect samples. 2023, NASA releases an independent review outlining updated mission designs and budget considerations. 2024, NASA announces a revised plan for the Mars Sample Return Mission, emphasizing innovation and international collaboration. Conclusion. The Mars Sample Return Mission is a landmark initiative in our quest to explore the Red Planet. With a budget of $3.1 billion and a collaborative approach involving NASA, ESA, and JAXA, the mission is set to return Martian samples by the early 2030s. Each of the four key phases, sample collection, retrieval, transportation, and analysis, presents unique challenges that require innovative solutions and international cooperation. As we stand on the brink of a new era in space exploration, the findings from Mars could redefine our understanding of life beyond Earth and inform future human exploration endeavors. The Mars Sample Return Mission, which is a collaboration between NASA, the European Space Agency (ESA), and the Japan Aerospace Exploration Agency (JAXA), plans to return samples from Mars to Earth by 2026 with a budget of approximately $3.1 billion. While the mission is being framed as a groundbreaking scientific endeavor, there are several counterintuitive elements that emerge from the information provided. 1. Budget reductions amidst complexity. The initial estimates for the mission's budget ranged from $8 billion to $11 billion, which were deemed excessive. The drive to reduce the budget to $3.1 billion seems counterintuitive given the mission's complexity, which includes landing on another planet, retrieving samples, launching them back into space, and safely transporting them to Earth. The expectation that such a complicated mission can be executed at a significantly lower cost raises questions about cost-cutting measures and their potential impact on mission safety and success. 2. Accelerated timeline. The mission is set for a return in 2026 with the possibility of earlier returns in the 2030s. This accelerated timeline contradicts the historical trend of planetary missions, which often face delays and complications. The optimism towards achieving such an ambitious goal in a compressed timeframe is notable, especially in light of the challenges faced by previous Mars missions, which frequently encountered technical and logistical hurdles that extended their timelines. 3. International collaboration versus national priorities. While the mission emphasizes the importance of international collaboration through the Mars Task Force, there is an inherent contradiction in how national priorities may influence the mission's execution. Each agency has its own objectives and constraints, and the tension between collaborative international goals and individual national interests may complicate the mission's coordination. The degree to which collaboration can withstand these competing interests remains uncertain. For scientific value versus budget constraints, the mission is touted as a high priority for understanding Mars and the potential for life. Yet the substantial budget constraints might lead to a compromise in the scientific rigor and thoroughness of the sample collection and analysis processes. The notion that high scientific value can be achieved within a reduced budget could lead to an underestimation of the resources necessary for comprehensive analysis. 5. Technological innovation as a cost reduction strategy. The call for innovative designs to achieve cost reductions presents a paradox. While innovation is often celebrated as a means to enhance efficiency and reduce costs, the integration of new technologies can also introduce unforeseen risks and complexities. The reliance on innovative solutions raises questions about the balance between innovation and reliability, particularly in a mission that involves unprecedented steps in space exploration. 6. Revising historical perspectives. The mission represents a significant shift from traditional Mars exploration paradigms, which have historically focused on remote sensing and in situ analyses. The counterintuitive aspect lies in the fact that returning samples from Mars could potentially yield more valuable insights than decades of robotic exploration, despite the inherent risks and challenges associated with sample return missions. 7. Potential for risk underestimation. The confidence expressed by NASA and its partners in successfully carrying out the mission might obscure the inherent risks involved, particularly those related to the complexities of extraterrestrial operations. The ambitious nature of the mission, coupled with the expectation of success within a challenging timeline and budget, could lead to an underestimation of the risks involved, which may impact mission planning and execution. 8. Long-term goals versus immediate outcomes. The mission's focus on immediate sample return as a means to prepare for future human exploration of Mars contrasts with the long-term nature of space exploration, which often requires sustained investment and patience. The expectation that a single mission can significantly advance our understanding of Mars and facilitate future human exploration may overlook the incremental nature of scientific discovery and exploration. These counterintuitive elements highlight the complexities and challenges associated with the Mars sample return mission, emphasizing the need for careful consideration of the trade-offs involved in such a high-stakes endeavor. The interplay between budget constraints, technological innovation, international collaboration, and scientific objectives will ultimately shape the mission's trajectory and outcomes. The Mars Sample Return Mission (MSR) represents a significant milestone in space exploration with its collaborative efforts involving NASA, ESA, and JAXA. While the overall mission's scope, budget, and phases have been well documented, certain nuances and details often overlooked can provide deeper insights into its implications and significance. 1. International collaboration and its challenges. One of the most crucial yet understated aspects of the MSR mission is the extent and complexity of international collaboration. The formation of the International Mars Architecture for Return of Samples (Mars Task Force) highlights the necessity for a unified approach among various space agencies. The integration of diverse engineering practices, scientific objectives, and budgetary constraints from multiple countries can lead to significant operational challenges. Significance. The collaborative nature of the mission underscores a shift in how space exploration is approached, moving from national pride to shared goals. The lessons learned from this partnership may set precedents for future international space endeavors, including lunar missions and deep space explorations. The complexities of aligning different agency cultures, methodologies, and expectations cannot be overstated. Many previous missions faced delays or failures due to misalignment among international partners. 2. Budget constraints and innovation. While the revised budget of approximately $3.1 billion is a focal point, the journey to this figure is equally significant. NASA Administrator Bill Nelson's acknowledgement of the initial estimates ranging from $8 billion to $11 billion indicates a critical need for innovation and cost-effectiveness. This necessity is framed within a larger context where budgetary constraints are becoming increasingly common in large-scale scientific endeavors. Significance. The drive to innovate under financial pressure may lead to technological advancements that could benefit other sectors beyond space exploration. For instance, the quest for cost-effective solutions may yield breakthroughs in materials science, robotics, and automated systems which can translate into practical applications on Earth. Furthermore, The need to expedite the mission timeline while adhering to budget constraints encourages a culture of efficiency and creative problem solving within NASA and its partners. 3. The technical feasibility of sample retrieval. The mission's technical complexity is often mentioned, but a detailed examination of the retrieval process reveals a series of unprecedented challenges. Successfully launching a vehicle from the Martian surface to return samples to Earth is a first in space history. The detailed engineering requirements for such a launch, considering Mars' lower gravity atmospheric conditions and the need for precision, are monumental. Significance: this technical feat will not only demonstrate advanced engineering capabilities but also enhance our understanding of planetary return missions. The methodologies developed could be applicable to future missions to other celestial bodies like Europa or Titan. By overcoming the intricacies of Martian sample retrieval, the scientific community could pave the way for more ambitious exploratory missions that require sample return capabilities. 4. Scientific implications of return samples. While the scientific value of returning Martian soil samples is well discussed, the broader implications of these findings are often overlooked. Analyzing these samples will not only provide insights into Mars geology and potential for past life but also offer critical data on planetary formation and evolution within our solar system. Significance: the MSR mission has the potential to reshape our understanding of planetary science and astrobiology, fields that have implications for understanding life beyond Earth. The results may also inform future missions aimed at human exploration, as understanding Martian soil's composition will be vital for assessing its suitability for human habitation and resource utilization. 5. The cultural and educational impact. The excitement surrounding the Mars sample return mission may also lead to an increased interest in STEM science, technology, engineering, and mathematics fields among younger generations. The collaborative nature of the mission, showcasing teamwork among nations, presents a compelling narrative that could inspire future scientists and engineers. Significance: by fostering a global perspective on science and exploration, the MSR project may help cultivate a more inclusive and diverse scientific community. The educational outreach stemming from this mission can contribute to a more scientifically literate society, which is crucial as we face global challenges that require innovative thinking and collaborative solutions. 6. Ethical considerations in sample collection. As we prepare to collect samples from Mars, ethical considerations surrounding planetary protection and contamination are critical yet often underrepresented in discussions. Ensuring that Earth-based life does not contaminate Martian samples, and vice versa, is a significant concern for scientists. Significance: addressing these ethical questions is essential for maintaining the integrity of scientific endeavors and for upholding the principles of planetary protection. The decisions made now will set precedents for future missions to other celestial bodies, reinforcing the importance of responsible exploration in an increasingly crowded solar system. Conclusion: the Mars sample return mission stands at the intersection of innovation, collaboration, and scientific inquiry. While the primary objectives and logistics are often highlighted, the underlying implications and challenges present a richer narrative that deserves attention. By focusing on international cooperation, budget, innovation, technical challenges, scientific implications, cultural impact, and ethical considerations, we can appreciate the mission's significance beyond the surface. As we venture forth into this new era of exploration, recognizing these subtleties will be crucial for the mission's success and its broader impact on humanity's quest to understand our place in the universe. The Mars Sample Return Mission (MSR) is an ambitious project set to be implemented by 2026, involving NASA, the European Space Agency (ESA), and the Japan Aerospace Exploration Agency (JAXA). With a budget of approximately $3.1 billion, this mission aims to collect and return Martian soil samples to Earth, paving the way for groundbreaking scientific discoveries about Mars's history and potential for life. Here are 4 key points for in-depth analysis and discussion. 1. Complexity of sample retrieval and transportation. The MSR mission is marked by its unprecedented complexity, particularly in the sample retrieval and transportation phases. The operation will involve the Perseverance rover, which has already begun collecting samples since its landing in 2021. The next steps include landing a retrieval vehicle on Mars, safely collecting the samples and launching them back into space, an operation that has never been executed before in space exploration history. This point raises critical discussions regarding the engineering challenges posed by Mars's unique atmosphere and gravity. The mission must address how to safely land on the Martian surface, navigate the terrain, and ensure that the samples are not contaminated during collection or transport. Innovative design solutions and risk management strategies will be essential for the mission's success, making this an important area of focus for both scientific and engineering communities. 2. Budget management and cost reduction strategies. The initial budget estimates for the Mars sample return mission ranged from $8 billion to $11 billion. However, NASA's current goal is to streamline costs to approximately $3.1 billion. This focus on budget management is critical, especially in light of the fiscal constraints that many space agencies currently face. The emphasis on cost reduction raises questions about how to balance ambitious scientific goals with the practical realities of funding. Discussions can focus on the methods NASA is employing to lower costs while maintaining mission integrity, such as leveraging innovative technologies, collaborating with international partners, and possibly soliciting proposals from the private sector. The mission's success may depend heavily on these strategies, making it a vital aspect of the overall project. 3. International collaboration and its implications. The role of international collaboration in the MSR mission cannot be overstated. The establishment of the International Mars Architecture for Return of Samples (IMARS) task force signifies a concerted effort among spacefaring nations to align their missions and objectives. With representatives from NASA, ESA, JAXA, and other countries, this collaboration is essential for integrating scientific and engineering challenges to meet the mission's objectives. This point opens up discussions on the benefits and challenges of international cooperation in space exploration. It raises important questions about governance, resource sharing, and the pooling of expertise from diverse agencies. Furthermore, the collaboration emphasizes the significance of collective scientific advancements and the potential for shared discoveries that can benefit humanity as a whole. 4. Scientific value of return samples. Finally, the scientific value of returning Martian samples to Earth is a cornerstone of the MSR mission. The analysis of these samples will provide critical insights into Mars's geology, climate, history, and potential for past life. This data is crucial not only for understanding Mars but also for informing future human exploration of the planet. This point allows for a rich discussion regarding the implications of the findings from the return samples. What specific scientific questions do researchers hope to answer? How could this data influence our understanding of life beyond Earth? The potential discoveries could reshape our knowledge of planetary evolution and the conditions necessary for life, making this an exciting area for ongoing research and exploration. Conclusion. The Mars sample return mission represents a significant milestone in space exploration, characterized by its complexity, budgetary challenges, international collaboration, and potential scientific breakthroughs. Each of these points merits in-depth discussion and analysis, as they not only highlight the intricacies of the mission itself but also reflect broader themes in the field of planetary science and exploration. The successful implementation of this mission could have far-reaching implications for our understanding of Mars and the potential for life beyond our planet. 1. The Apollo Program 1961–1972. The Apollo program was a series of space missions conducted by NASA with the goal of landing humans on the Moon and bringing them safely back to Earth. The program included a total of 17 missions, with Apollo 11 being the first to successfully land astronauts on the lunar surface in 1969. The program's implementation involved extensive international collaboration, advanced technological development, and significant funding. culminating in the return of lunar rock and soil samples that greatly advanced scientific understanding of the Moon's geology and the solar system. 2. The Viking Program 1975 to 1982. NASA's Viking program consisted of two spacecraft, Viking 1 and Viking 2, launched to Mars to conduct a detailed study of the Martian surface atmosphere and potential for life. The missions included landers that performed experiments on Martian soil and returned data and images back to Earth. Although the primary aim was not to return samples to Earth, the program laid the groundwork for future Mars exploration missions, including the Mars Sample Return mission, by providing crucial insights into Martian conditions and the challenges of operating on the planet's surface. 3. The Hayabusa missions 2003 to 2010, 2014 to 2020. The Hayabusa and Hayabusa 2 missions, conducted by JAXA, were pioneering efforts to collect samples from asteroids and return them to Earth. Hayabusa successfully retrieved samples from asteroid Itachi and returned them in 2010, while Hayabusa 2 collected samples from asteroid Ryugu and returned them in December 2020. These missions demonstrated advanced technologies for sample collection, transportation, and return, and they provided valuable insights into the early solar system, significantly influencing the design and planning of future planetary exploration missions, including the Mars Sample Return mission. Future outlook: predictions for the Mars Sample Return mission by 2026. The Mars Sample Return mission (MSR) is poised to revolutionize our understanding of the red planet and its potential to harbor life. As we look ahead to its implementation by 2026, several key predictions can be made regarding its impact, technological advancements, and international collaboration. 1. Technological innovations and developments. The complexity of the Mars Sample Return mission will necessitate significant technological innovations. By 2026, we can expect advanced robotics. The operational phases will likely see the deployment of highly sophisticated robotic systems capable of navigating the Martian terrain autonomously. Enhancements in AI-driven decision-making will allow these systems to perform critical tasks with minimal human intervention. Launch and retrieval technologies. The mission will pioneer technologies for launching payloads from another planet, a feat never before accomplished. Expect developments in propulsion systems that can efficiently transport Martian samples back to Earth, which could also have applications for future interplanetary missions. Sample containment and preservation. New materials and containment technologies will be developed to ensure that the samples are preserved in pristine condition during their transit back to Earth. This will be crucial for maintaining the integrity of the samples, which will be subject to rigorous scientific analysis upon arrival. 2. Scientific discoveries and insights. Upon the successful return of the Martian samples, scientists will be able to conduct unprecedented analyses that may lead to groundbreaking discoveries. Understanding Mars history. The returned samples will provide insights into the geological history of Mars, including its past climate and the presence of water. This will help scientists construct a clearer picture of Mars' evolution and its potential to support life. Search for life. One of the primary objectives of the MSR mission is to search for signs of past life. The analysis of organic compounds and microfossils within the samples could yield evidence of ancient Martian life, reshaping our understanding of life's existence beyond Earth. Resource utilization for future missions. The mission's findings will inform future human exploration efforts by identifying resources available on Mars, such as water and minerals, which are essential for sustaining human presence. 3. International collaboration and partnerships. The collaboration between NASA, ESA, JAXA, and other international partners will set a precedent for future space missions. Strengthen global framework. The success of the MSR mission will reinforce the framework established by the International Mars Architecture for return of samples in Mars, highlighting the importance of cooperative efforts in space exploration. Shared knowledge and resources. This mission will foster a culture of shared scientific knowledge and resources, with participating nations pooling their expertise and technology to solve complex challenges. This collaborative model could serve as a blueprint for future international space initiatives. Increased funding and investment in space exploration. As nations witness the advancements and potential scientific returns from the MSR mission, we can anticipate a surge in funding and investment in space exploration programs globally, leading to a new era of discovery. 4. Public interest and engagement. The Mars Sample Return mission is likely to capture the public's imagination and inspire a new generation of scientists, engineers, and explorers. Educational initiatives. Anticipate a range of educational programs aimed at engaging students and the public in the mission's objectives. Interactive platforms and outreach activities will help demystify space exploration and foster interest in STEM fields. Media coverage and public discourse. As the mission progresses, media coverage will likely increase, highlighting milestones and discoveries. This will stimulate public discourse on the implications of finding life beyond Earth and the ethical considerations of planetary exploration. Cultural impact. The mission's success could lead to a cultural renaissance in how humanity views its place in the universe, potentially influencing art, literature, and philosophy as we grapple with the implications of extraterrestrial life. Conclusion. The Mars Sample Return mission represents a monumental step in our quest to explore and understand Mars. With a budget of $3.1 billion and a collaborative international effort, its successful implementation by 2026 will not only advance scientific knowledge but also pave the way for future explorations. The technological innovations, scientific discoveries, strengthened international partnerships, and heightened public interest surrounding the mission will have lasting implications, shaping the future of space exploration for decades to come. As we anticipate the return of Martian samples, we stand on the brink of a new era of discovery that may fundamentally alter our understanding of life and the universe.